All right, welcome to Chem 313, Lecture 1. And this is the summer of 2020 edition of Chem 313. So we're going to be going rather fast this quarter if you've never taken a 5-week summer course before. So be prepared to watch and review these lectures more than once per day. What we're going to talk about in today's lecture is it's material that is hopefully review for you. We're going to talk a bit about the organization of living matter, very briefly. We'll get to that in more depth in later parts of the course. The most important thing that we're going to cover today is a review of intermolecular forces, which you've seen in general chemistry, but they tend to de-emphasize it in organics, so I'm hoping that I can refresh your memory with that section. And we're going to talk a little bit about solubility, because that topic tends to go hand in hand with intermolecular forces. The most important thing that we're going to be covering today, and if you get nothing else out of today's lecture, then this is what you should understand, is you need to understand hydrogen bonding, and you need to understand the hydrophobic effect, which are both examples of intermolecular forces. And hydrogen bonding and the hydrophobic effect reign supreme over biochemistry. These subjects underlie almost all biochemical interactions that we're going to talk about. So if you can understand these two topics, you should be well positioned going forward into the future of this course. All right, so let's talk a little bit about living matter before we go any further. So biochemistry is usually defined as the chemistry of living matter. And that raises the question of what is living matter? What do we have? What properties can we point to say that this blade of grass is living matter, whereas this rock is not living matter? And it's kind of a philosophical point, but there's usually a cluster of different characteristics that living matter has that non-living matter does not have. So the first thing that living matter tends to be is organized. And this slide shows the way in which living matter tends to be organized. It tends to be organized in roughly a hierarchy of complexity, and we'll talk about that in a moment. Secondly, living matter tends to be functional, which means that all molecules or all substances have a function or a job to do. So everything that is involved in living matter has its place. There are a few oddball substances like waste products that don't really have a role, but those are more the exception. Almost everything in a living system is going to have some sort of a function. A third property of living matter is that it tends to convert energy and also other matter, and by other matter I mean non-living matter or formerly living matter, into useful forms. And so what do I mean by useful forms? I mean something that is functional and has a job. So in other words, living matter tends to assimilate other matter from its environment and energy from its environment and use them for its own use. The fourth thing that living matter tends to do is it tends to reproduce itself. And it tends to do so well, but not perfectly. So that's a topic we're going to get to at the end of the course when we talk about our biological information section. But the idea is that living matter can make copies of its own living matter so that we end up with more organisms. So in other words, we have population increase. But this process is not perfect. There's always going to be a few little errors in this process. And because of that, and because of the fact that energy and other living matter are limiting in most environments, living matter tends to evolve over many generations. So you never see evolution just by looking at a glimpse of living matter over a period of seconds or hours in a test tube. But if you look at multiple generations of living matter, it almost always evolves in such a manner so that living systems that are better adapted to their environment will persist, and other living systems that are not very well adapted to their environment will die off. We're not going to talk about evolution much in this course, but it's important to keep in mind that evolution shapes everything down to the shapes of individual molecules that is in a living organism. It's not just all about behavior, and it's not about, body morphology or anything like that. It works right down to the level of intermolecular forces. So let's take a look at the hierarchy of living matter. So what do we notice about all these biomolecules? Everything that's listed in green here is a subject that we're going to emphasize in this course. That doesn't mean that we're not going to be talking about organelles or anything like that. We do have to talk about those a little bit, but this is where the green is what we're going to emphasize. So at the lowest level of our hierarchy, we have molecules that we would call inorganic precursors. So these are not really living molecules. These are just molecules that can be put together to give you more complex molecules. They're inorganic, so water would be the most important one of these, but also things like oxygen and carbon dioxide. So these are molecules that you can stick together to make more important things. The thing about inorganic precursors is that they can undergo chemical reactions with each other to form more complex molecules called metabolites. Metabolites are all organic. And the usual definition of organic is they've got carbon-carbon bonds. So metabolites themselves are not terribly interesting molecules, but they have some sort of functionality. They've got different chemistry that they can undergo. And so if you take a few metabolites together, and once again, they undergo chemical reactions with each other, you end up with these molecules we call building blocks or monomers. Now, we're going to talk more about building blocks later in the week. But the key thing about building blocks is they have some structural diversity and they have complementary functional groups, which we'll talk about later. And what that means is that the building blocks or the monomers can react with each other, once again, chemical reactions here, to give us large molecules that we call macromolecules or polymers. So these are the molecules that do most of the real work in living systems. These are things like nucleic acids, DNA, proteins. Certain complex carbohydrates count as macromolecules or polymers. And macromolecules or polymers come from variable joining of building blocks. And what we mean by that we'll get to later on in the week. Now, macromolecules or polymers can then associate together to give us supramolecular complexes. So these are groups of macromolecules that work together So we're talking about things like the ribosome or transcription factors or, the membrane, big complicated structures that are made of many, many molecules. One important point to note is that on going from macromolecules to supramolecular complexes, we don't have chemical reactions we have reversible binding of our polymers by non-covalent intermolecular forces. So this is an important distinction between biochemistry and other branches of chemistry. Earlier chemistry, basically all we cared about was forming covalent bonds, right? Chemical reactions. Biology and biochemistry, we do care about covalent bonds, we do care about chemical reactions, but we care more about binding. And that's where most of the interesting stuff happens. It's not formation of bonds, it's formation of intermolecular forces. And then if you keep going with this, by more reversible binding interactions, your supramolecular complexes can associate to give you organelles, which can then associate together in a single outer membrane to give you an overall cell. And then, of course, in multicellular organisms, you can keep going even further. So we said before that intermolecular forces are sort of king in biochemistry. So intermolecular forces in this course are going to be much more important than covalent bonds. So what exactly are intermolecular forces? We would define these as attractive forces. By definition, they're always attractive between molecules and in most cases they are due to attractions between partially positive and partially negative portions of those molecules. All right, there is one exception to that. The exception is the hydrophobic effect, which we'll talk about later. And the hydrophobic effect is not due to attractions between partially positive and partially negative portions of molecules, at least not directly. The hydrophobic effect is driven by a different sort of force. So an important thing to notice about intermolecular forces is that they are always much weaker than covalent bonds. All right, so to give you an example, the free energy of a hydrogen bond, we'll talk about that, what that is in a moment here, is on the order of minus 20 kilojoules per mole, whereas the energy of a covalent bond, I mean, it's very variable, depends on what two atoms you've got bonded together, it's on the order of minus 200 kilojoules per mole. And a hydrogen bond is one of the stronger intermolecular forces. So intermolecular forces are at least 10 times weaker than covalent bonds. So where do these forces come from? So you can imagine you have one sort of molecule over here. We'll call this molecule A. We'll have some other molecule we'll call molecule B. And you can have a situation in which we'll say molecule A has one side of the molecule that has sort of a deficit of electrons. So because of that, the nuclei on this side of the molecule are somewhat more exposed and you have somewhat of an excess of positive charge, which means that you'd have an excess of negative charge elsewhere. And then on molecule B, you may have one side where there's an electron excess, so that there's an abundance of negative charge on that side of the molecule. And because of that, these two molecules would attract one another. Now, this electron excess and this electron deficit can take many different forms, and it doesn't even have to necessarily be a permanent thing. But as long as there is some situation like this where you've got an excess of positive on one molecule and an excess of negative on another, you have an attractive intermolecular force. Now, one of the things that you may want to recall from basic physics is that the force of attraction between these two molecules is going to be proportional to the two charges divided by the distance between them squared. D is the distance between these two particles. And it's proportional. There's a proportionality constant in front that we're not going to show here. So Q1 and Q2 are the charges on the particles, including the sign, and D is the distance between them. And you'll notice that if Q1 and Q2 have opposite charges, then that means the force is negative, which we define as an attractive force. Now, in biochemistry, we don't usually care about forces. What we care more about is energy. And it's easier to visualize energy if you think of it as work. So once again, from physics, work is equal to force times distance. And so if you take the force multiplied by the distance, you would end up with the work it takes to separate these two particles being proportional to, once again, Q1 times Q2 over the distance, this time not squared. And so you can think of this as the work needed to separate the particles. And once again, if the number that you get is negative, that means that the force is attractive and work must be done. It doesn't happen by itself. So also from physics, work under constant temperature conditions is defined as enthalpy, or H. So enthalpy is usually defined as the heat absorbed or released by a system at constant pressure. We're not going to talk about that a whole lot in this course, but I set up enthalpy as something that we're going to contrast with a different form of energy later on. Here's the take home. A higher magnitude of charge or a shorter distance between the two particles adds up to a stronger intermolecular force. And by stronger, we mean higher energy. So regardless of which intermolecular force you have, if you have a higher magnitude of electrical charge on either of your two particles, or they're closer together, that intermolecular force will be stronger. So let's review the intermolecular forces that we're going to encounter in this course. The first two I'm going to sort of blast through because they're not that important in biology. And then the last ones we're going to talk about in much more depth. All right, so the first sort of intermolecular force that you need to know is the London force, or the dispersion force. This is the weakest of all the intermolecular forces. You don't need to know a whole lot about this intermolecular force because it's not all that important in biology. It is important if you want to understand things like melting points and freezing points and the behavior of gases, but biology doesn't take place in the gas phase, at least not on this planet. So what is a London force or dispersion force? It's a temporary attraction between induced dipoles on the surfaces of molecules. So what's an induced dipole? Well, you can imagine that we have two molecules that look like this. And inside each molecule, you've got nuclei that are connected to one another by covalent bonds through the electrons. And on the outside of these molecules, you've got this electron cloud, so to speak, where your electrons are just occupying the space around the nuclei, but there's some variability in their position. And because there's variability in the position of the electrons, you can end up in a situation where you've got a slight temporary electron excess on one side of the molecule and an electron deficit on the other side. And that means that you will end up with a partial negative charge on the side of the molecule with an electron excess and a partial positive on the side with an electron deficit. So what that means is that the next molecule lying next door to this one, as soon as this molecule, the first one, experiences this change in its position of electrons, now we've got this partial positive charge that is going to pull on the electrons on the second molecule so that now it has an electron excess on one side. And now we've got a partial positive and a partial negative together, so we have an attraction. So all molecules do this. However, it's the only type of intermolecular force that you see in free atoms or in nonpolar molecules, right? So in nonpolar molecules are ones that have no polar bonds. Or it has polar bonds whose dipoles cancel. So now might be a good time to review the whole electron geometry versus molecular geometry stuff that you covered in general chemistry. All right, so London forces are weak. And the reason that they are weak is because they're temporary. They only exist for a second, and then the electrons just go back to the way they were before, and we no longer have an attraction. The next level up in strength is the dipole-dipole force. So dipole-dipole forces are different from the London force in that these are permanent attractions. The dipole-dipole force is an attraction between partial positive and partial negative charges that are permanently there on your molecules. And the reason for that is because the molecules are polar. So the dipole-dipole force is something that you see in polar molecules only. So for example, acetone is a classic example of a polar molecule. Acetone is this. So we've got this central carbonyl group where the oxygen, because it's much more electronegative than carbon, is going to tend to pull the electrons towards it, and the carbon is kind of left with a deficit of electrons. So as a result, we have a partial positive charge on the central carbon and a partial negative on the oxygen, which is what we see over here. And that means that the oxygen on one acetone will be attracted to the central carbon on the other acetone. That is a dipole-dipole force. So these are stronger than London forces. They're only present in polar molecules. However, they're not all that important in biology except in a special case that we're going to see on the next slide. All right, so now we get into stuff that's really, really important in biology. So the hydrogen bond is the next level up in strength of intermolecular forces. So the hydrogen bond is really just a special type of dipole-dipole force. A hydrogen bond is an extra strong dipole-dipole interaction between a non-bonded electron pair on an electronegative atom, for the purposes of this class, nitrogen, oxygen, or fluorine, and a hydrogen atom also bonded directly to nitrogen, oxygen, or fluorine. Here's what I mean by that. For a hydrogen bond, you need to have one of these. You need to have an OH, an FH, or an NH. And you need to have a lone pair on one of those same elements. And what you end up with is a situation that looks something like this. So for the sake of argument, I'll draw a hydrogen bond between an OH and a fluorine. So notice that oxygen is highly electronegative, so it's going to tend to pull electrons toward itself. Hydrogen is not. So that means that our oxygen will have a partial negative. Hydrogen has a partial positive. Okay, so far so good. This is starting to look like a dipole-dipole force. Well, our fluorine over here is going to have a partial negative, and it's going to be bonded to other stuff, of course. Let's not worry about that just yet. So because of this partial positive and partial negative, we have an attractive interaction between the hydrogen and the lone pair. That is what we would call a hydrogen bond. So in this diagram over at the right, I've shown a hydrogen bond between two molecules of hydrogen fluoride. So it can be between two molecules that are different. It can be between two molecules that are the same. It doesn't matter. The important thing to note is that the hydrogen bond is the interaction between the hydrogen atom on one molecule and a lone pair on the other one. The molecule that has the hydrogen on it is said to be the donor, and the molecule that has the lone pair on it is said to be the acceptor. Right? And of course, one molecule can be acting as both a donor and acceptor for two different hydrogen bonds. That's also possible. Now, there's a common misconception, and that is that some people think that this bond here is the hydrogen bond. Not true. That is a covalent bond to hydrogen. The hydrogen bond is non-covalent. Now, why is a hydrogen bond so strong? It's stronger than a regular dipole-dipole force. Well, there's two reasons for that. First thing is the fact that the delta plus and the delta minus tend to be of large magnitude. Why is that? Well, that's because fluorine and oxygen and nitrogen are very highly electronegative. So they tend to pull electrons towards themselves very strongly. So that's one reason. Another reason has more to do with quantum mechanics, and that is that we have an orbital overlap factor where if this is, we'll say, our nitrogen with a lone pair, so this is our acceptor, that non-bonding electron pair occupies this big open orbital. And if we have a hydrogen atom plugged into it, the hydrogen atom has an s orbital, which is going to be partially empty because it's bonded to a highly electronegative molecule over here. And so the hydrogen atom kind of gets its orbital filled up with electrons from the acceptor, and that increases the strength of this bond. Another thing to notice about hydrogen bonds is that they are stronger if they are straight. What I mean by that is this. Let's say that this is our donor and this is our acceptor. All right, so notice that this one, all three atoms are in a straight line. This is going to be stronger than a hydrogen bond that looks like this. That one is weaker. Why is that? Well, that's because of this orbital overlap factor that I just illustrated over here. In the case of the straight line hydrogen bond, we get this really good orbital overlap between our non-bonding pair and our hydrogen atom. In the case of a crooked or bent hydrogen bond, you get much less overlap. So hydrogen bonds are extra strong intermolecular forces between polar groups that involve a hydrogen atom. They're stronger when they are straighter. They're also stronger the more electronegative your acceptor molecule is. So in other words, fluorine to hydrogen is going to tend to give you a stronger hydrogen bond, all else being equal, than nitrogen to hydrogen. For examples, I refer you to worksheet 1. All right, the fourth type of intermolecular force, still stronger than even hydrogen bonds, although much more variable than hydrogen bonds. This is what we would call ionic interactions. And this isn't a single intermolecular force, it's a family of intermolecular forces. So this is whenever you have a partial charge and a complete charge, or two complete charges. So for example, if we had a positive charge with an attraction to a partial negative charge, this is what we would call an ion dipole interaction. And if we had a positive and a negative ion together, this is what we would call an ion-ion interaction. So these are strong intermolecular forces, again, because of the fact that the magnitude of charge is going to be high. You've got a complete electrical charge on at least one of your particles. And ionic interactions, especially ion dipole interactions, are responsible for the solubility of many ions in water. So look at what happens if you take sodium chloride and dissolve it into water. Whenever you dissolve an ionic compound in water, it splits up into ions. We end up with a positive sodium ion, and what's going to happen is that the water molecules all around it are going to organize themselves so that the negative ends of the dipoles are pointing in towards the positive sodium ion. So each one of those dotted lines is an ion dipole interaction. And this is a strong intermolecular force. And then for the chloride, it's exactly the opposite. Chloride is negative, and so the water molecules will orient themselves so that the positive end of the dipole faces inward towards chlorine. And again, we have a strong ion dipole interaction in that case. We'll also see in many molecules interactions between a positive ion and a negative ion together. So this is what we would call an ion-ion or an ion pair interaction. There's a special type of ion pair interaction that we'll talk about in proteins called a salt bridge, and I'll define that one later on, but that's a special case of ion pair. So you can think of this as almost like an ionic bond if you believe in the term ionic bond. Chemists don't really like that term. But ionic interactions are quite strong, and they're important in biomolecules. Now, there's a fifth intermolecular force that you need to know about, but before we talk about that one, we have to talk about solubility. Solubility makes the fifth intermolecular force a bit easier to understand. So if we were talking about dissolution, what are we talking about? When you're mixing a solvent and a solute together and one dissolves in the other. So whenever you have something dissolving in a solvent, we have four things that are happening all at the same time. First of all, the intermolecular forces between the solute molecules break apart. Same thing happens to the solvent. They mix, and then they form new intermolecular forces. So you can think of it like this. Let's imagine that this is are solute. And we want to dissolve it in a solvent. So what we have to do is we have to separate up the particles. So if you have a crystal lattice, like it's a solid or whatever, you're going to have to break up the intermolecular forces that are holding these particles together. Now, we've done that. Let's move on to the same thing for the solvent. So for the sake of argument, I'm going to draw our solvent as a liquid, but of course it doesn't have to necessarily be a liquid. Same thing has to happen. You have to break apart the intermolecular forces holding those molecules together. So that we now have separated solvent molecules. The third thing that we do is we mix them. So that now we've got expanded solute and solvent molecules occupying the same space. And then in our last step, we condense them so that we form new intermolecular forces. Something like that. And we now have a solution. Now, obviously, not everything is going to be soluble in everything. Not every solute will dissolve in every solvent. So we say that a solute is soluble in a solvent if the sum of these four processes is, I'm going to put this term in quotes because we're going to be using it a lot in this course, is favorable. What does favorable mean? Favorable means spontaneous. And spontaneous means that the change in Gibbs free energy for that process is negative. So in other words, what that means is that on going from our pure solute and our pure solvent to the mixture, we have a decrease of free energy. So generally speaking, if we say that a process is favorable, this is true for anything in this course, you can think of that as meaning the delta G for that process is negative. So are these processes generally going to be favorable? Well, let's imagine you're going to break up the intermolecular forces between solute molecules. Well, typically, that's going to be unfavorable, right? Because you have to break up intermolecular forces. Same thing for the solvent. Then you have to mix the solute and the solvent molecules together. So depending on the situation, this is usually going to be favorable. There's cases where it's not. And then you form new intermolecular forces, so that's typically going to be favorable because you're getting new intermolecular forces back. All right, there we go. So does that mean that this process is going to be spontaneous, or is it going to be favorable? Well, generally speaking, this whole process is going to be favorable if the sum of the new intermolecular forces is stronger than the sum of the original intermolecular forces, with some exceptions, which we're going to see on the next slide. So this is the origin of that rule that like dissolves like. If you have two substances that are pretty similar, then probably they have similar intermolecular forces, which means they can form similar or stronger intermolecular forces with each other in a solution as they would by themselves in the pure compounds. So to summarize this slide, a solute is said to be soluble in a solvent where dissolution is spontaneous if the overall delta G of dissolution is negative, and this usually occurs when the solute to solvent intermolecular forces are as strong or stronger than the solute-solute and solute-solvent intermolecular forces. But there are exceptions. I'm going to give you guys an example of a case where there's an exception. All right. There's an important thing to notice about water. Water must form hydrogen bonds with water. So whenever you're in liquid water, every water molecule is going to be participating in, on average, 4 hydrogen bonds. And because these hydrogen bonds are so strong, it is energetically unfavorable to break them up. So the water molecules are always going to be hydrogen bonding with 4 other water molecules whenever you have liquid water. Now, let's say that you're going to dissolve a polar solute in water. So let's say you take a polar substance like sugar and dissolve it in water. Well, the solute is now going to hydrogen bond with the water. So what we've done is we've replaced a water-to-water hydrogen bond with a water-to-solute hydrogen bond. Okay, water is happy, right? Because we have not lost any hydrogen bonds to water. But what about if you take a nonpolar solute? So for example, let's do hexane. Hexane's a hydrocarbon. There's nothing there but carbon and hydrogen, which have about the same electronegativity. So it cannot form hydrogen bonds. So if we were to put hexane in water, what would end up happening is that water can't hydrogen bond with it. And therefore hydrogen bonds would be lost. And that would be unfavorable because the hydrogen bonds are so strong. Okay, so what happens then if you pour hexane into water? Well, once again, water must form 4 hydrogen bonds. And if it can't form those hydrogen bonds with the solute, what it's going to do is something like we see in this picture right here. What's going to happen is that our water molecules, because they can't hydrogen bond with the hexane, are going to hydrogen bond with each other. And to do that, they have to form this very particular shaped structure that surrounds the hexane molecule. I'm not going to completely complete the picture there, but you get the idea. So if our water molecules are oriented like this, the waters can still hydrogen bond with each other when they have this particular arrangement. So this arrangement is what's called a clathrate. It's where you have water molecules arranged around your solute molecule in a very specific pattern. Okay, now, what do you suppose the favorability of this is? What do you think the delta G of this sort of arrangement is? Well, I refer you back to the definition of delta G. For the free energy change for any process is delta H, the enthalpy change of that process, minus the temperature times the entropy change. The enthalpy part of the delta G comes from the intermolecular forces. So we said before that the delta H of this process, we have hydrogen bonds being formed. So our enthalpy is going to be, change is going to be negative because we are forming favorable intermolecular forces. We're forming hydrogen bonds. However, our change in entropy on forming this structure is also negative. And that's because we have to adopt this very particular pattern of hydrogen bonds. So generally speaking, if your system is going from disorganized to organized, your delta S is going to be negative, and that is unfavorable. A negative delta S gives you a positive second term for your delta G, and it tends to push your delta G up. So because of entropy, formation of this structure around all of our dissolved nonpolar solute molecules is unfavorable, and the system is going to avoid it as much as possible. So how does this work out if you actually take hexane and dissolve it in water? What's going to end up happening is that the nonpolar solute is going to clump up when it's in liquid water. And the function of the clumping up in liquid water is that it minimizes the surface area in contact with water so that we end up with as few ordered water as possible. Right? Because if you have a bunch of separated hydrocarbon molecules surrounded by water, we have lots of ordered water around the surface of every single one of these molecules. But if we clump them all together into a single particle or droplet or something like that, then we get to liberate water molecules that would have been stuck on the inside, and we have fewer organized waters around the droplet than we do around dissolved molecules. And this is what we call the hydrophobic effect. It's the property of nonpolar molecules that causes them to cluster in water in order to minimize the size of the water cage around the nonpolar substance. The hydrophobic effect is a property of water, not of the solute. So you do not see a hydrophobic effect in the gas phase. You do not see a hydrophobic effect in a nonpolar solvent. It's not that the molecules are attracted to each other. That's a common misconception. It's that the nonpolar molecules are squished together by the water because the water is trying to minimize the loss of entropy associated with forming this rigid clathrate. So to summarize the strength of our intermolecular forces and factors that influence them, okay, All intermolecular forces are going to be stronger in a less polar environment, or lower dielectric constant is a way that you could phrase that. Why is that? Well, let's say that we've got an ion-ion interaction. It could be dipole-dipole, it doesn't really matter. But if we're in a nonpolar environment, then there's no positive or negative charges around to sort of dilute these charges. So the only charge interaction that they experience is due to the other particle. Whereas if we're in a polar environment, what's going to happen is that we're going to have partial negatives interacting with our positive charge and partial positives interacting with our negative charge. And so this attractive force will be very strong, whereas this attractive force is going to be weaker because each of these molecules is also being pulled in different directions. You can think of it as like a vector sum sort of thing. Dipole-dipole forces and hydrogen bonds, they tend to be stronger with a greater difference in electronegativity, right? And that's because you get a greater magnitude of your charge. And once again, higher magnitude of charge, stronger intermolecular force. Ionic interactions also are stronger with the higher magnitude of charge and with the shorter distance, right? Same thing is true for hydrogen bonds as well. So for example, the ionic interaction between a 2 plus and a 1 minus charge is going to be stronger than the interaction between a 1 plus and a 1 minus charge. Hydrogen bonds are stronger if they're shorter and straighter. We already talked about why that is. And then overall, you can summarize the strengths of intermolecular forces in the order that we show on the bottom there. Dispersion is the weakest, followed by dipole-dipole, followed by hydrogen bonds, followed by ionic, and then covalent bonds are much stronger than any of those. The hydrophobic effect kind of varies. It can be anywhere on this continuum. It depends on the size of nonpolar surface area that becomes buried. So it's not easy to say where hydrophobic would fall in this scale. All right, regardless of what intermolecular force you have, though, it's important to note that all of these are weak forces. All intermolecular forces are much weaker than covalent bonds. And this is important in biology because it means that intermolecular forces can form reversibly. And because intermolecular forces are reversible, all interactions involving weak intermolecular forces can be easily manipulated by changing your environment. So for example, temperature, pH, etc., can change the magnitude of your intermolecular forces. So temperature is an obvious one. Higher temperature means that you've got more molecular motion, and therefore you've got more kinetic energy. And the more kinetic energy your molecules have, the less they're going to attract each other because they're going to be bouncing off of each other all the time. pH can also affect the strength of intermolecular forces. We'll get to that in the next lecture. Exposure or orientation of a chemical group. So in other words, the shape or the conformation of your molecule can affect the strength of an intermolecular force. And we're going to see examples of that going forward. Concentrations of other substances, for example, salts or acids or bases, can affect the strength of your intermolecular forces as well. And this is important because it means that the function of biomolecules, which is related to their intermolecular forces, can change in different situations. I'll give you an example of that to conclude the lecture, and that is the protein lysozyme. So lysozyme is an enzyme. It's a protein, so it's a big, complicated macromolecule. This enzyme tends to function best between a pH value of 6 and 7. So that's what this graph over here is trying to show, is that we have maximal activity between pH 6 and 7, and then if you go lower in pH or higher in pH, the activity of the enzyme drops off. It loses its ability to function. The reason for that is that the acid or the base disrupt intermolecular forces. That alters the shape of the molecule in such a way that the function is impaired. How that works, we're going to start to look at beginning in lecture 2, which we will talk about in the next presentation. And so in the meantime, I refer you to some practice problems on homework 1 and worksheet 1.